Great. Thanks, Debbie, for the introduction. So this is Byron Blackmore speaking. I'll be taking you through the new features in Simcenter Flotherm 2019.1. A little later in the webinar, my colleague Paul Rose will take over to take you through what's new in Flotherm XT 2019.1. So let's begin. The first feature I would like to introduce is called Boundary Condition Independent Reduced Order Models. Before we get into it, just a bit of background. So reduced order modeling has recently been getting a lot of interest in the electronics cooling industry. There are various methods that are out there. We've done something new and exciting in Flotherm, but first let's set the stage. So reduced order modeling is an approach or a collection of approaches that could be used to derive a dynamic compact thermal model from a thermal simulation model. The objective is to create a model that can be solved much faster while maintaining predictive accuracy in space and time. So the diagram along the bottom shows this conceptually. So we begin with a Simcenter Flotherm model, which really is a very large system of n equations that has to be solved to produce a temperature prediction. We go through a reduced order model extraction process to compress this into a much smaller system of our equations. And because the system of equations is much smaller, it can be solved much faster, sometimes orders of magnitude faster than the original Flotherm model. So fast is not always better, of course, so we need to maintain accurate results. So we want a reduced order model to be capable of producing temperature predictions that are very similar to what we observed in the original Flotherm set of results. So let's describe the approach taken in Flotherm 2019.1. So the method selected for implementation of Flotherm is known in industry as the fantastic method. The fantastic method is a methodology that was introduced by Professor Lorenzo Codicasa, who is pictured here. And I've provided a list of the most relevant publications in this area that describe the method in detail and provide several validation examples. So everything we've done in Flotherm is based on this work. So let's take a look at the workflow of the fantastic Rom method. So we'll begin with the diagram on the right. The inputs to the fantastic method are a discretized model, and that means you have a Simcenter Flotherm conduction model that has a reasonable grid distribution assigned to it. The other inputs are an acceptable relative error, which is a measure of how close we want the reduced order model results to be to the original Flotherm model results, and a heat transfer coefficient range over which we expect accuracy. Those are the inputs. We go through an extraction process, and the output is a reduced order model that is boundary condition independent within that heat transfer coefficient range that was nominated. So some of the key characteristics of this fantastic Rom method, number one is that it's boundary condition independent. So you can place this reduced order model in any thermal environment downstream, provided it's within the heat transfer coefficient range that was nominated as the input, and you will maintain predictive accuracy in space and time. The fantastic Rom method supports any number of heat sources. The errors associated with the fantastic method are mathematically bound and related to that acceptable relative error input that we see on the right, the details of this relationship are found in the original publications. And very important to note that the CFD solver is not used during the extraction of the reduced order model, which allows us to create these Bci Roms very quickly. This is what it looks like inside the software itself. So it's an option under the project menu. So we choose to export the project, choose Bci Rom. We have access to the inputs I described in the previous slide, so we can choose the acceptable relative error, and we can nominate the heat transfer coefficient range that should be used. We go through an extraction process, and the result of which is a Bci Rom. This is provided in the form of a set of matrices that are compatible and solvable downstream in tools like MATLAB or Octave. Now, as this is brand new functionality to our user base, it's the first time we've supported this type of output from Flotherm. We wanted to provide as much validation information as possible to supplement the validation work that was done in the original publications. There is a full validation report available on Support Center. It directly compares results from Simcenter Flotherm to the results from a solved Bcr Rom across a wide range of applications and a wide range of boundary conditions. So in total, there were 5 different models used with 200 heat transfer coefficient scenarios, and altogether this represented over 5,000 temperature versus time curve comparisons. And using the default Bcr Rom settings for acceptable relative error and heat transfer coefficient range, the average error across those 5,000 curve comparisons was 0.248%, and the maximum error observed was less than 1%. So very impressive technology. I would encourage you to review this validation document if you want to learn more. Here's a quick preview of one of the examples within the validation report. So in this case, we're looking at an IGBT module. It has 18 heat sources, which you can see in red in the image, and 3 ambients. So an ambient condition for the cold plate on the bottom. We have another ambient for the top heat transfer coefficient, and the other remaining 4 phases are encapsulated with this outside world ambient condition. So what we see on screen is a randomly selected scenario with various values of these heat transfer coefficients. So this represents our test case. The curves that we see on screen, all of the solid lines are the Simcenter Flotherm results, and the dotted lines are the results from the Bci Rom. And visually, you can see the curves, they practically lie on top of one another, so an excellent result. In reality, there's a little bit of deviation, so the maximum error in this particular case was 0.151%, so it was a great result. I want to point out that the x-axis is on a log scale, and this is intentional, as we want it to illustrate the level of agreement it holds for all time constants that are exercised throughout this comparison. So it performs well in the microsecond range, it performs well at steady state. So you should have a lot of confidence that you could drop this in any application and get accurate results. So in terms of what you can do with Bcr Roms, so the most obvious application is to perform extremely fast transient analysis. So the workflow in this case is the first step obviously is to create your Bcr Rom using Simcenter Flotherm. You then specify what heat transfer coefficient should be active and specify power as a function of time. So in this case, we have 4 heat transfer coefficients and 9 power dissipations and a sinusoidal variation in power. You run this downstream in MATLAB, for example, wait a few seconds, and the results will appear on screen. The results that appear on screen are going to be within that specified relative error of Simcenter Flotherm, and up to 40,000 times faster. So that was the best improvement in calculation time that we observed. 40,000 times faster, it's a big number, difficult to understand, so we put together this visual aid to help you. So for a long-haul commercial flight, so for example, a flight going from Shanghai to Chicago, a commercial flight would take 14 hours. If that went 40,000 times faster, you'd arrive just over 1 second later. So this represents an incredible increase in productivity and time savings when running transient analysis. Let's look at a worked example. We'll look at an IGBT module. In this case, I'd like to take note that the starting point for a Bcr Rom export is a calibrated Simcenter Flotherm model. I believe there's little point in creating a very accurate Bcr Rom model of a Flotherm model that does not match reality. So I think this is always the starting point for a workflow, is to create an accurate Flotherm model backed up with experimental data. Once we have that, the process is to specify which heat sources are active and add reasonable grid to the model. So in this case, we're going to be working with 4 active heat sources, and the total number of grid cells was 4.6 million. So using the Bcr Rom Extraction command, using the default settings, so a relative error of 0.001, to create the Bcr Rom took 2 hours and 40 minutes. As it turns out, this time was very well spent, and we'll see why in a few moments. The next step, now that we have our Bcr Rom, is to specify a power dissipation profile for the heat sources in the model. So in this case, we'll specify a power profile from an automotive test cycle, UDDS FDP 72 drive cycle, which begins with as a velocity versus time specification. We transform that into inverter power versus time, which you can see as the red curve on screen. So it's a very complex power profile, so many changes in power dissipation spread out over about 1400 seconds. So this becomes an input to the ROM. We solved this in MATLAB and we were able to produce accurate temperature versus time data for all of the heat sources in the model, and the Bci Rom solve took 2 minutes and 33 seconds, which turns out to be about 40,000 times faster than it would have taken to solve this power profile in the original Flotherm model of that IGBT. So very useful. So the next application for Bcr ROMs is to use the results to help design power control strategies. So built into the MATLAB and other tools are very sophisticated controls for control systems. Perhaps the most well-known one is a PID controller. This ties in nicely with Bci Rom solves within MATLAB, as they can be solved in faster than real time in many cases. So if you're not familiar with this, the inputs to a PID control system would be a temperature set point, and that's the black dotted line that we see at 90 degrees Celsius in the various charts. And in this case, we're modifying the PID control constants, so Kp, Ki, and Kd, hoping to get a satisfactory response. So we're controlling power attempting to reach that set point. So both extremely fast transient analysis and power control systems are good applications for Bcr ROMs downstream. Next, let's look at how this works in the software with another example. So here we have a Simcenter Flotherm model of a package-on-package device. We have two stacked BGA packages. The prerequisites for the Bcr Rom extraction, the first of which it has to be set to conduction only. Check, we've done that. We need to have at least one heat source present. We use the find tool to select the heat sources that are present. So we have two in this case. If we look down at the geometry, we can see it's centered. We'll quickly flash on wireframe to show you where that sits. We need to have a reasonable grid assigned to the model, so we'll turn on the display of grid. We can see we have a localized grid space around the heat sources, so we should capture those gradients very well. So that is good. We also need to have at least one heat transfer coefficient defined in an ambient attribute, so we can visualize what is attached to the current model. So on the boundaries, we have there are three different ambients that are defined in this model: sides, top, and bottom, and each one of those ambient conditions has a heat transfer coefficient assigned to it. One last thing before we begin: the temperatures that will be predictable by the Bcr Rom when we solve it downstream. First of which will be the centroid of every heat source in the model. So we had two, we saw that a few seconds ago. It will also let you predict the temperature of every monitor point in the model once you have your Bcr Rom. So in this case, for this model, we have an array of monitor points, both on the top die and also on the bottom die as well. So we have 11 monitor points present, and the results for each of those monitor points will be solvable by the Bcr Rom when we have it available. The next step is to actually create the Bcr Rom. So that's a project command, export project Bcr Rom. We have control over those inputs described previously: acceptable relative error and the heat transfer coefficient range. Hit OK to begin the process, assign an appropriate name, and then the Bcr Rom extraction process will begin. So while we're waiting for this extraction process to complete, this Flotherm model has been solved already. It's a transient application. The power dissipation is a pulse function. I just want to put this results up on some screen. So it's a monitor point plot for the transient set of results that will compare to the results of the Bcr Rom in a few moments. Okay, now that we have a Bci Rom in place, we'll start up MATLAB and I'll show you what kind of results you can get by solving with Bci Rom. So this is already set up. We're pointing to the appropriate location. So this is where the Bci Rom zip file was extracted. Just want to point out, if you're not proficient with MATLAB at this point, we have provided an example solver harness which would allow you to This example will allow you to specify power dissipation, overall transient duration. This is available on the Support Center download page for Simcenter Flotherm. It comes with a brief instruction manual as well. So this is all set up with the same power dissipation profile that was found in Flotherm. All I have to do now is hit solve in MATLAB. It'll take a couple of seconds to produce the results. This example is pre-configured to show a plot of temperature versus time, surface heat flows versus time, mean temperatures at the surfaces versus time, and a reminder of what the power dissipation was. Close down the other ones and just focus on the temperature prediction. So that took a few seconds to calculate using the Bcr Rom, which was several orders of magnitude faster than using Simcenter Flotherm in this particular case to look at the results. So if I make a tile that plot, and we'll go back and look at the results in Flotherm. They are a virtual match for one another. So we get very accurate results that agree extremely well with Flotherm, but in a fraction of the time. The next feature in Flotherm 2019.1 is called thermal netlist extraction, which is very closely related to the Bcr Rom extraction feature we just discussed. So thermal netlist extraction is aimed at enabling electrothermal circuit analysis downstream. Electrothermal effects have become a very important design issue for the electronics industry. More and more, the impact of temperature on circuit performance has to be accounted for. So what we see on the right is a comparison. We're looking at on top is a uniform temperature assumption in a circuit simulation tool. So uniform temperature, we have a perfect current waveform, so no degradation, sharp corners in the waveform, for example. However, when we begin to introduce temperature variation to the circuit simulation, a lot of interesting things happen. So this has got the same example with temperature variation. The current waveforms look a lot different, so a different amplitude and a non-constant signal. So these changes can be important enough to cause undesirable behavior in the circuitry, and it can be enough deviation to cause the circuit to fail to meet spec. To address this problem, we've introduced the ability to create a thermal netlist from a conduction Simcenter Flotherm model. So this works in a very similar way to the Bcr Rom technology. In fact, it uses the same fantastic Rom technology behind the scenes. So the user would create their Flotherm model, export a project, and choose thermal netlist. There is one important difference. For a thermal netlist extraction, the only input is the acceptable relative error. So this the resultant thermal netlist will work for the conditions of the original Flotherm model. It will create a reduced order model behind the scenes and then transform it into a thermal netlist format. Once you have the thermal netlist in hand, the next step in the workflow is link it to an electrical netlist or a circuit description, and then use a tool like Mint or Eldo to perform electrothermal analysis downstream. So once the analyst has completed the electrothermal analysis in Mint or Eldo, they can use the results for several reasons. The first of which is to ensure the circuit will operate properly in the installed environment. The second of which is to help debug unexpected circuit behavior, such as the current ratio mismatch that we see on screen. And finally, to ensure that various industry standards are met before releasing the product. Both Bcr Rom and thermal netlist export are licensed features. Just a quick note on licensing. So both Bcr Rom and thermal netlist require a license. The same license key will unlock both. If you want more information, please reach out to your local account manager. Okay, the next topic is called frequency-based power control. Frequency-based power control allows power design strategies to be deployed by defining a set of operating frequencies for a device or for a heat source. The way it works in the software is that the user is able to work with a new controller attribute. This attribute consists of a table of defined frequencies. So each frequency that is defined has a temperature range over which it will operate. So the user defines a low value and a high value for temperature. each one of these frequencies also has a power versus temperature curve, which we can see on the chart at the bottom right. So frequency, temperature band, and also this power versus temperature curve definition all constitute the definition of a controller attribute. So this controller attribute can then be linked to a new type of object within Simcenter Flotherm, which is called a controller object. Within the controller object can exist exactly one heat source, and this heat source is the power that will be controlled by the controller, and one monitor point, and this represents the temperature sensor for the controller. The controller object is always associated with a controller attribute that we saw on the previous slide. So remember, that's our definition of various operating frequencies for the device. The user can also specify what the start frequency is for the simulation. And that's it in terms of the inputs. So as Simcenter Flotherm is solving a transient analysis, all of this information is taken into account, and you will get results that look similar to this. The monitor point temperature is recorded at each time step. And if that sensor temperature is greater than the maximum temperature at the current operating frequency, then the controller will take one step down the frequency table. So we'll go to the next lowest frequency in that case. If the sensor temperature is less than the minimum temperature, then the opposite happens. So the controller will take one step up in the frequency table and move to the next highest defined frequency. And the way this is just a set of typical results. So we're looking at an application processor in a mobile device. For the early transient, it simply follows the frequency definition. So it begins at the maximum frequency, about 2.8. After about maybe a second, it encounters the maximum temperature for that frequency. It drops down one level, keeps increasing in temperature until it has to drop down to 1.5 gigahertz. And after this point in time, we sort of have this semi-stable looping where the frequency jumps from 1.5 to 1 gigahertz. This application is actually it has other components that are surrounding that processor. So the other components begin to heat up as well at t equals 0, and eventually they induce a large enough impact on the sense temperature that the controller has to drop down to another semi-stable state where it jumps back and forth between 1 and 0.5 gigahertz. So we can drop this controlled power heat source into any Simcenter Flotherm environment and application to explore various options for power control strategies. And the last bit on 2019.1 is just a few words on model supply chain. Specifically, the ECXML format, which has become more popular for the past couple of years. So a bit of history first. ECXML was jointly developed by Mentor Graphics and ANSYS in 2016 to help support the thermal model supply chain between Flotherm and IcePack. So the original scope of the format was that it would support objects that are common to both Flotherm and IcePack. In 2018, it was mutually agreed to open the format to address the needs of our customers and industry to support better model sharing between a broader range of tools. So to represent that change in Flotherm 2019.1, both import and export of ECXML is available by default. And previously that was a separate download from Support Center. And it no longer requires a license to export an ECXML file. On the Simcenter Flotherm XT side, the latest release, 2019.1, will support the import of ECXML. And speaking of Flotherm XT, so now is the time which we'll pass the presentation over to my colleague Paul. Over to you, Paul.
Thank you, Byron. This section will introduce a new feature of the Simcenter Flotherm XT software which enhances the design space exploration and optimization by making use of external third-party optimizer software. Once a thermal analysis in Simcenter Flotherm XT is complete, you are presented with a single snapshot of a design. Many questions may still arise. For example, a simple "what if I change this?" or, at the other end of the spectrum, what is a perfect optimum design? It is essential that a user can quickly and easily make changes and then set up subsequent runs. Currently, our user base has access to two methods of parametric study: manual variation and design of experiments, better known by the abbreviation DOE. In the first method, the user must manually define the values of any parameters that they wish to study. This could include geometry dimensions and smart part properties such as the number of heatsink fins or a change to the material applied to parts of a model. The individual scenarios are set up with these values. Alternatively, DOE can be used. In this instance, a user will simply define the minimum and maximum range for two or more parameters, define the number of scenarios to create, and the software will automatically fill in data to create the best coverage of a design space. A cost function can be added to drive the software towards an optimum, and response surface modelling can be utilised to numerically predict the results in the gaps. While this is a tried and tested method, the downside is that you may need a large number of experiments to accurately fill the design space and obtain sufficient resolution in the response surface. So, while Simcenter Flotherm XT includes tried and tested optimizer tools, there are other methods from other tools. To allow users to benefit from such tools, Simcenter Flotherm XT 2019.1 has a new feature to communicate parametric settings to such external optimizer tools. The new option, External Optimizer, has been added to the parametric study area. It is also worth mentioning that to aid usability, when a project contains any parametric study already defined, the appropriate button is shown depressed, giving an instant indication to the user. Once the study has been activated, the user is able to set up the input and output variables for the study. For the input, you are not limited to numerical entries such as dimension, as a number of these external optimizers can accommodate input to say the material applied to a part. It is possible to define an ad hoc or linear step variation, as in a manual variation of a range as in DOE. Usually the output variables are left as just recording the value. Cost functions for the optimization process are usually set in the external tool. It is also often possible to define constraints on the input or to define a study to say minimize my heatsink weight, but ensure that the junction temperature does not rise above 90 degrees C. Once the parameters have been set up, it is then simply a case of creating a task file which can then be imported into the external optimizer tool. Scenarios are generated and passed back to Simcenter Flotherm XT for solution. Results are shown in the scenario table and also passed back to the optimizer tool. One such external optimizer tool is HEEDS. HEEDS includes a state-of-the-art optimizer process called Sherpa. This is proprietary design space exploration functionality that is used to simultaneously leverage multiple global and local search strategies and adapt the search as it learns about the design space. HEEDS fits effectively with Simcenter Flotherm XT model setup. This method requires no model simplification or model fitting. Using the hybrid adaptive intelligence search allows you to find better designs in fewer evaluations, ultimately reducing product development costs and product design risks. To fully exploit the benefits of HEEDS driving Simcenter Flotherm XT, a new portal was made available in HEEDS 2019.1.1. The portal drives the new external optimizer interface in Simcenter Flotherm XT to modify the input parameters. The settings of these made in Simcenter Flotherm XT are automatically imported to HEEDS, run the design scenarios and extract the results without requiring any scripting from the user. In summary, using HEEDS linked to your Simcenter Flotherm XT model helps you reduce effort finding optimum design solutions, but also provides valuable insight into product design alternatives to drive down development costs and risk.